Okay, everyone, here we are for the second part of the video lecture for Chapter 23 on linear regression, or inference for regression, rather. So in the first part of this video lecture, we were talking about, or we sort of ended last time talking about checking for a significant slope. And really, that's one of the main points about regression inference, if you recall. Okay, so when we're checking for a significant slope, what we're really doing is saying, well, is that slope significantly different from zero? So our null hypothesis here is going to be that our population slope, or the slope for the population relationship between our explanatory variable x and our response variable y, is going to be zero. The alternative hypothesis is simply that it's not zero. In a one-sided sense, we could have a slope that's greater than zero. We could have a slope that's less than zero as an alternative. Those are both one-sided because we're specifying a direction, either greater than or less than. Here, however, we could have a two-sided alternative where we say the slope is simply not equal to zero, which means it could be positive or it could be negative. But to do that, we have to calculate a value of t, right? We have to calculate a critical value of t. And that's what we're going to use to find our p-value on table C. So testing for a significant slope is really a one-sample t-test. It's a one-sample t-test that we've done. What we have to do, though, is basically quantify the amount of spread in our scatter of data points, okay? And the way we do that is through the standard error of the slope. Standard error of the slope. The standard error of the slope is the standard deviation of our y data. This is our regression standard error. That's the standard deviation of our, or in our response variable, divided by a measure of the variation in our explanatory variable, our x variable. So it's a ratio of variation in our y data to variation in our x data. All right. If we have a large standard error of the slope, that means we have a lot of spread, both horizontal and vertical, in our data. But mostly this is referring to vertical spread along the y-axis, right? If we have a, so you can imagine, for example, if your regression standard error, the variation in your y data, is large compared to the variation in your x data, you do this math, that would give you a large ratio, a large number for standard error of the slope. In the previous video, we talked about a large standard error of the slope means a lot of spread in your data. That means a lower correlation, a lesser correlation between your x and y variable, okay? If, however, we have very little spread in our y data, you divide that by a larger amount of spread in your x data, and you get a small standard error of the slope. All right, why is that important? Because to calculate t, we take the slope of our regression line and divide it by the standard error of the slope. If you have a large standard error of the slope, lots of spread in your data, and you divide a small slope by that, you end up with a small value of t. And a small value of t should equate to a large p-value. However, if you have a small standard error of the slope, very little vertical variation in your data, you divide that by a large slope, then you get a large value of t, which should give you a small p-value. All right. Okay, so let's take a look. This example here was the frog mating call example that we talked about. So a couple of things about this data table that you see here. This is the regression output that you would see in Minitab. First of all, you have the equation of your line, of your regression line. So frog call mating frequency would be equal to our y-intercept plus the slope multiplied by some temperature value. All right. Down here, we have the data output. Now there are two rows here. This first one, called constant by Minitab, is always your y-intercept. And we don't really care about that one. We care about the slope, which is our second line. Now, this value is our regression standard error. Okay, so that is basically the standard deviation in your response variable along the y-axis. All right, here we have our slope, and here we have the standard error of the slope. All right, so if we take our slope, and divide it by the standard error of the slope, we get our t-value. So 2.33 is a slope divided by a standard error of the slope of 0.3468 gives us a t-value of 6.72. Well, that t-value is essentially saying that we have 7 standard deviations away from our mean under our null hypothesis. So our slope, our actual value of our slope, lies 7 standard deviations away from our null hypothesis slope of 0 on the frequency distribution of sample slopes. Well, 2 standard deviations, a t-value of 2, will give us about 95% confidence. This is way beyond that, so that's why our p-value is effectively 0. We also see we have an r-squared adjusted of about 70%. That means that our x data, x value variable, right, temperature in this case, explains about 70% of the variation in frog mating call frequency. So that's a pretty good predictive model there. Okay. All right. So here's the calculation again for t. We have our slope divided by the standard error of the slope, 6.721, with degrees of freedom of sample size of 20 in this case, minus 2 of 18, and minus 2 equals 18. We can look it up on table C and we find that our p-value is going to be less than 0.001. The furthest value to the right on that row, degrees of freedom 18 in the table, is 3.922. Well, we have a t statistic of 6.72, so it's way to the right of that, and your p-values get smaller as you go to the right, so all we can say from the table is that our p-value is less than 0.001 with a two-sided test. That's very highly significant. So that means we have a significant relationship between temperature and frog mating call frequency. All right, down here you see the actual p-value calculated by Minitab. It's effectively 0. Okay. Let's look at table C. So we're looking at degrees of freedom of 18, and we're looking for a t-value of 6.721. So degrees of freedom of 18 right there. You go all the way to the right, and our last value is 3.922. Well, 6.7 whatever it was is way over there to the right, so we know that our p-value is less than 0.001 that you see there at the bottom for two-sided p. Okay, so it's a highly significant relationship. All right, so when we're testing or doing statistical inference for linear regression, where we're testing whether or not our slope is equal to 0, what we're really doing is testing for a lack of correlation. Okay, so back in chapter 3, we talked about the correlation coefficient, R, which was a measure of the strength of the relationship between an x and a y variable, between an independent and a dependent variable, an explanatory and a response variable. And so that value of the correlation coefficient could range between -1 and +1. The closer to 0, the less strong the relationship. The further from 0, either towards +1 or towards -1, the stronger the relationship. Okay, we can calculate the slope if we know what the correlation coefficient is right here. So R is our correlation coefficient. If we know the standard deviation of our response variable and the standard deviation of our explanatory variable, we take our correlation coefficient and multiply it by the ratio of those two. That gives us our slope. So if our correlation coefficient is 0, it doesn't matter what this ratio is, anything multiplied by 0 is 0. If your correlation is 0, your slope is 0. So that's at the sample level, right? The population parameter for the slope is beta, and that's related to the population correlation coefficient, what we call rho, and when beta equals 0, rho equals 0. So at the population level, this is simply a way of saying that if we have 0 correlation, our slope is 0. And hopefully we can tell that from our sample. So when we're testing the hypothesis that our population slope equals 0, it's the same as testing the hypothesis of no correlation between our explanatory and response variable. All right, let's look at an example here, one we haven't looked at before. This is a scatter plot of the relationship between height or stature in meters and hand length. All right, so take a look at this. There's not a really clear pattern. I mean, if you didn't have that data point right there, which might be an outlier, you could say, well, maybe you have a positive relationship. But with that data point included, is this apparent relationship, weak as it is it significant? So we put this data into Minitab, we run a regression, and we get our output here. Here's our equation. Hand length in millimeters equals 126 plus 36.4 times height. Again, this is our y-intercept. This is our slope. That's our x variable height, all right? Okay, now take a look at our second line here. This is the slope line. So we have our slope of 36.41. We have a standard error of the slope of 21.91. That's a measure of how much spread we have, right? We divide our slope by the standard error of the slope. We get a t-value of 1.66, and that correlates to a p-value of 0.113. That's less than 2, isn't it? So we know we're less than 95% confident, so our p-value is going to be greater than 0.05. And so this is telling us we should accept our null hypothesis. There is no significant relationship there. All right, r-squared value adjusted, use that one, about 8.1%. This tells you that height is not a good predictor of hand length. So that's a very low r-squared. This means that of all this variation in hand length, only about 8% is explained by height. And that's borne out by a non-significant p-value, okay? I mean, you could draw a regression line through that, but there's so much, vertical variation in this data that the next sample could very well give you a negative slope. There's a lot of sort of wobble room or wiggle room in that slope because there's so much vertical variation in the scatter of our data points. And that's what that non-significant p-value and very, very low r-squared is essentially telling us, okay? All right, so again, we're using regression ultimately to be able to predict some value of y, call it y hat, a predicted value, from some value of x, assuming we have a significant relationship, all right? You don't want to predict or use an equation, for a linear regression equation, to predict if you don't have a significant slope. That means there's not a strong enough relationship to predict. So if your p-value is greater than your alpha, you don't want to predict, okay? All right, let's assume that we do have a significant p-value. What we're trying to do is to predict within range. Remember, we talked about in chapter 4 how if you're predicting beyond the range of your x-axis and your y-axis data, you're extrapolating, and that's dangerous because you're assuming that the relationship remains linear beyond the range of your data, and that's not a safe assumption to make, okay? So, to estimate an individual response for a given value of x, we're going to use what's called a prediction interval. A prediction interval tells us how likely an individual measurement is to fall within some range along the y-axis. Prediction intervals are about individual values. Remember that. It's important. So if we randomly sampled many times, there would be many different values of y. Many values of y along the y-axis for one value of x, all right? So we'd have many different values of y obtained for a certain value of x, and those values of y should follow a normal distribution with the average right at the predicted value on the regression line, right there. Okay, so a prediction interval then is going to tell us what the likelihood is of any single measurement falling within this interval. So usually we have a 95% interval, or 95% prediction interval, okay? So if we define that interval, say between this point and this point, we know that one measurement, one single measurement, has a 95% chance of falling within that interval. All right, now let's look at the confidence interval for the mean response of our y variable, the average response. Confidence intervals are always about sample averages, okay, or averages. Prediction intervals are about individual values. So we might also want to predict the population mean value of y, our mean response, for any value of x within the range of our data. So, using inference, we calculate a level C, usually 95%, confidence interval for the population mean response when x takes a specific value. So, this interval is centered again on the predicted value of y, okay? And that predicted value of y is an unbiased estimate of the population mean response. It's an unbiased estimate of our population mean response. the true value of the population mean response at a given value of x will be within a confidence interval in some percentage of all intervals computed. So if we have a 95% confidence interval, then the mean population response right there would be within that interval 95% of the time. All right? Okay. So let's take a look. You can tell Minitab on a scatter plot where you've included the regression line, you can tell Minitab to include a prediction interval, which is the red line, and a confidence interval. And usually we do 95%, right? So 95% confidence interval, 95% prediction interval. So look at our prediction interval, which is the red line. Notice that it's wider, right? It goes from here, for example, down to there. It's wider than our confidence interval, which is the blue dashed line. Why is that? Because a prediction interval is only about a single measurement, and individual values can fall further away from the mean of the population along the x-axis of a frequency distribution than a sample mean can. Remember central limit theorem, or law of large numbers rather. The larger the sample you have, the closer the sample average is to the population average, right? So you're not going to very likely get a sample average that falls, all the way to the tail end of a distribution. But an individual value certainly can fall all the way to the tail end. And so your prediction interval is going to be wider than your confidence interval. Confidence intervals are always about sample averages, right? So what we're saying here is that a single measurement would fall within this 95% interval, but a sample average would fall within this confidence interval, okay? So with our frog call frequency data, the confidence interval for the mean call frequency at 22 degrees Celsius is between 43.3 and 46.9. So at 22, we have 43.3 and 46.9. The sample average is going to fall within that range 95% of the time. The prediction interval for an individual call frequency at 22 degrees Celsius is 38.9 to 51.3. So an individual measurement would fall between 38.9 here and 51.3 95% of the time. All right. Okay, now it's possible you could have a value that falls outside that because this is only 95%. There's a 5% chance that an individual measurement would fall to one side or the other, all right? Okay, so confidence intervals and prediction intervals are again a way to qualify our estimates of sample means and individual measurement values, and they're important. All right, let's look at this example. So one we've seen before, number of beers consumed versus blood alcohol content. Okay, so blood alcohol content is a function of alcohol consumed for a random sample of 16 adults. Is the relationship linear? Look at the spread of the data. Seems to fall within a straight line sort of channel, so it's linear. What do you predict for 5 beers consumed? So for 5 beers consumed, we would say an average of maybe 0.07, 0.08, something like that. All right, so we have our equation of that line right here, okay? Blood alcohol content equals our y-intercept plus our slope times number of beers consumed. Sample size 16, we see a correlation coefficient of 0.89, square that to get your r squared, coefficient of determination, 0.8. So number of beers consumed explains 80% of the variation in blood alcohol content, as you would expect. It should. That's pretty good. All right. So again, we have our slope row in our table. This is our slope, 0.0179, or 0.018, we could say. The standard error of the slope is 0.002. You divide your slope by the standard error of the slope, you get a test statistic of 7.5. That's really high. That's why your p-value is so small. That means that in the distribution of all the possible slopes, that slope falls 7 standard deviations away from the average if our null is true. Well, we only need 2 standard deviations to be 95% confident, so that's really confident. That's why our p-value is so small. Question was, what do you predict for 5 beers consumed? You can tell Minitab to predict. You can plug in a value of 5, for example, and it will tell you that should equate to a blood alcohol content of 0.077. And that makes sense. 5.077 right there. And our 95% confidence interval is that the average blood alcohol content for 5 beers consumed would fall between 0.066 and 0.088 95% of the time. Now, what about an individual measurement of 5 beers? So for one person who consumed 5 beers, we're 95% certain that that individual value would fall between 0.03 and 0.12 blood alcohol content. Okay, so a wider prediction interval, narrower confidence interval. Again, individual value for prediction interval, a sample average for confidence interval. Okay. Okay, last thing here, let's talk about the conditions for inference. So just like with any other test we've done, there are certain conditions that our data have to meet in order for us to be able to use regression, right? First of all, our observations have to be independent. That means, for example, in the blood alcohol content example, you couldn't have individuals in your sample who agree to drink a certain amount of beer, the same amount of beer, let's say. That would bias your results. They have to be independent random samples. The second is that our relationship needs to be linear, and we'll talk about how to figure that out here in a minute. The third is that the standard deviations of our y response variable is the same for all values of x. This is just a way of saying that the width of these hypothetical distributions should be the same for individual values of x. I'll show you how to test for that. Finally, our response variable needs to vary normally around its mean. That's just a way of saying that we need to have normal distributions here for all possible values of y. And I'll show you how to test for that as well. All right. First tool in your toolkit for assessing the validity of your data for regression is called the residual plot. Okay? So remember, the residuals are how far each data point falls from the predicted value, the regression line value. A residual plot plots your residuals against a zero line. The zero line actually is your regression line. You should have about the same number of values above it as below it, and they should have sort of an even distribution, right? No obvious sort of increasing or decreasing spread of values, okay? And I'll show you more about this in a second. But if the residuals are scattered randomly around zero with uniform variation, no more here than here than here, for example, that's an indication that your data are linear, okay? That you have normally distributed residuals for each value of x, and that you probably have constant standard deviation for any given value of x. So let's look. Here are 3 different residual plots. This is basically what you want to see, right? So notice that you have about the same vertical variation for any value of x, all right? And it appears to be in essentially a straight line pattern. That's good. Here, you have a problem. Here, notice that we have a curved pattern to our data. This is a strong indication that we don't have linear data. It does suggest that we have about the same standard deviation in our response variable for any value of x, but the data is nonlinear. Well, you can't run linear regression on nonlinear data. At this point, you'd be justified in stopping your analysis and not going any further with linear regression. You should watch for that, especially maybe, I don't know, in a homework assignment I might give you. Third, we have another problem here. Notice how we have this sort of expanding pattern of variation. You have very low standard deviation here. Here you have a large standard deviation. So this is a good indication that your standard deviations are not equal. You'd be justified in stopping the analysis and not going any further because you're violating one of the assumptions of linear regression. So this residual plot is very important. You should always do this before you embark on linear regression for your data. All right, some other tools we can use. Let's go back to our frog mating call example. With Minitab, you can produce, or you can tell Minitab to do what's called a 4-in-1 plot. And that's what you see right here. This whole thing is a 4-in-1 plot, all right? First part of it is called a normal probability plot. This is also called a normal quantile plot. We've done these before. remember you're plotting residuals here to see if they seem to fall in a straight line pattern. And by and large, these do. There's one possible problem point right there, maybe an outlier, but in general, they fall in a straight line. This is an indication that your data is linear. All right, you can also look at that with a histogram that you see down here, for example, right? And you see a fairly symmetric pattern indicating the data is normal, okay, normally distributed. All right, this is a Fitts plot. So here we have our residual plot. It's called a Fitts plot or a residual plot. But again, you don't see an obvious pattern to that. It's very, very random. Half the data points above, about half the data points below, sort of a random scatter shot, sort of shotgun blast kind of pattern to your data. Okay, that's good. And that's again telling us that our data is essentially normally distributed, right? This is saying linear, this is saying normally distributed, this is saying normally distributed. And then here we have basically a plot called an order plot that looks for any pattern that might be developing as our data points are collected. So we have our data points ranked along the bottom here in terms of those that were collected first and those that were collected last. If you see any sort of obvious pattern developing, right, something like this, oops, sorry, I'll go back. That's an indication that your data there's some bias in your data, maybe a systemic error, with using a laboratory piece of equipment or something like that. Maybe your first data points were good, but then an error happened in the machine, let's say, and you start to get data points that are deviating from this sort of random pattern. You want to look for that, okay? As long as you don't see an obvious pattern like this, then you're probably good. Okay, so definitely before you run any sort of regression analysis, whether it's in a homework I give you or your actual data that you're analyzing at some point in the future, you always want to assess it for those assumptions. And a 4-in-1 plot in Minitab is a great way to do that. All right. Okay, so that wraps up chapter 23 on linear regression.